The common ion effect is not a new concept for us. We did see it in previous equilibrium units. All right, so what is the scenario? Well, the scenario is that we are beginning with multiple substances in our beaker. And we have added substances that will play a role in the equilibria of either the weak acid, the weak base, or in this case, the insoluble solid. Okay, we're being asked to find, in this example, the solubility of silver chromate. Okay, so our silver chromate, always the solid on the reactant side, will be dissociating to give us 2 silver ions and 1 chromate ion. And then we understand that we can describe this with a KSP, solubility product constant, and it would be silver squared times chromate to the first. Okay, and we're given our KSP, which we know will be such a small value, 9 times 10 to the minus 12. Okay, so we understand that we have this in our solution, and we could visualize that it's going to be an insoluble solid, a solid that has fallen to the bottom. But look what else we have. We have a solution, and we know all nitrate compounds are soluble. So this solution is 0.1 molar silver ion and 0.1 molar of nitrate. So the question we have to ask ourselves is, does anything here play a role in our ice table? So we know our ice table. We don't keep track of the solid, but the solution gives us some initial silver. Now, we don't get influenced by our coefficients. We are told that we made this solution, or this is present in this solution. This is independent of the actual dissociation. And I don't have any information that I'm starting with any of this. Now, we are asked to find the solubility, and we know solubility is our X. Now, Le Chatelier's principle, I know that we could already forecast the impact on X based upon the initial presence of some silver. So we know this is going to work to get a certain amount of silver and chromate ions for equilibrium that will equal our KSP. But if we are already starting with some initial amount, we don't have to shift as much to the right. And so a common ion decreases the solubility of the given insoluble solid. We don't have to make as many ions. And so X will be smaller than if this were 0 and 0. Okay, so now we take into account the coefficients. So to get to equilibrium, I will add 2X and X. And so this is 0.1 molar plus 2X and X. I'm solving for X. So going ahead and plugging in. So this will be very careful, make sure that we're applying the correct exponents. So this is 0.1 plus 2x squared times x. Now our very small values, we can move forward assuming 5% rule, but we have to come back and check. So we do need to square this and then apply times x and so on. So just be careful with your math. But what we find here, x, which is the solubility of our silver chromate, is 9.0 times 10 to the minus 10th mole per liter. Remember, we're solving for brackets, and so that will be the unit. Can I share with you that if this were in pure water, So if we did not start with some common ion in pure water, the solubility of silver chromate is 1.3 times 10 to the minus 4th mole per liter. So look at that impact. That's a nice amount of silver ion. So it definitely had a great impact on decreasing the solubility. Okay, that is the common ion effect.